So welcome back. Welcome back to our discussion together. I hope you're enjoying this as much as I'm enjoying on recording them. Well, maybe there's other things that you could do that you would like a little bit better than have a conversation with me about, this time, solubility and miscibility. Okay, so here's one of my pet peeves that I really cannot stand for people to do. And that's in a class, maybe an instructor, maybe another student will use these two terms interchangeably, and they are not. These two terms are different, which is why we have these two terms. Solubility and miscibility are in reference to two separate ideas. Now, what is the difference? Because you know good and well, if I just told you it's one of my pet peeves, I'm going to probably slap it on a test. So get ready for that question because it will come your way. Solubility is the idea that a solid will dissolve in a liquid, something soluble. Okay, so one of my memories growing up, making Kool-Aid. Well, one of the things to make Kool-Aid, you add sugar. Okay, well, you had to add enough sugar, but only a certain amount of sugar could actually go into that solution before it wouldn't dissolve anymore. Well, that sugar is dissolving in the water. So therefore, the sugar is very soluble in the solvent, and that solvent in that case was water. Okay, so solubility is the concept that I can take something and I can dissolve it in water, aka making spaghetti water. One of the first things that I do when I make spaghetti noodle is that I take water, I put it into a pot, and I salt the heck out of it until it tastes like the ocean. That's the only way that you can flavor your pasta noodle. All right, so I keep adding salt. Salt will keep dissolving in solution, and we call that solubility. That is not miscibility. Miscibility it's in reference to two different liquids. And those two liquids mix together to give you a very uniform solution from top to bottom. This kind of goes back to something that we talk about that we refer to as like dissolves like. Actually, you can apply it to both of these terms, but especially in the term of miscibility. Because if I have a non-polar organic material and I put it in a non-polar solvent that is really organic-like in nature, then those two things should be miscible, and they should mix together very well without a problem. Polars and polars are the same way. And it's also one of those reasons that we say oil and water don't mix, people. You know that. Oil and water don't mix. It's all really due to like dissolves like, or like will actually dissolve like. Well, the problem here is that the word is dissolve, okay? So it really shouldn't be dissolve, even though that we know what they mean by that slogan. We know what they're referring to, but it should really be in terms of miscible. Oil and water are not miscible. I would never really want to say oil and water are not soluble. What do you mean soluble? What's getting dissolved? I mean, oil is already a liquid. Water is already a liquid. So you really shouldn't be using the term solubility for those purposes. That should be in reference to a solid that's getting dissolved in a liquid. Oil and water would be in reference to miscibility. All right, so in a laboratory environment, we often deal with these organic reagents that are liquids, and I've said that before. And these liquids are going to mainly be nonpolar. However, they could have some polar pieces that are associated with them that might slightly increase their polarity. It might help them to dissolve in something like water a little bit better. But again, I use the term dissolve, and it needs to be miscible. So dissolving is going to be one of those broad terms that's used even in a textbook, but if you really do want to be particular, you need to refer to solubility and you need to refer to miscibility. All right? Okay, so another term that I like to throw out is this term solvation, not salvation. All right, so solvation, Solvation, and it's when a molecule that is in point of reference is surrounded by solvent molecules. This helps break up the substance that we are studying and does what we would call either make it soluble or make it miscible. So whenever we get a molecule that we want to bring into the picture and really have a discussion with, and we dump that into, like, say, a beaker of water, all right, that beaker of water is going to have water molecules, and those water molecules will begin to associate themselves around that addition that we've just added in. And once that begins to happen, and once this hangout and relationship begins to form, we will call this a solvated material. And this is the process of solvation. So when molecules are surrounded by a solvent, that process is called solvation. All right, so solubility, miscibility, solvation. Now, another term that I will throw out here as well is something called hydration. Well, if you hydrate yourself, you are replenishing water, right? And some people, will use a term hydration in order to talk about this process as well. And what that really refers to is it's very specific to water molecules. So if we are using water, some people do use the term hydration instead of solvation in order to describe that process. Solvation is just any old solvent. This solvent could be water, but it could be other things as well, such as something that we call methylene chloride or dichloromethane. That is a solvent that's used in a laboratory quite often. Toluene. Toluene is a solvent that's used in a laboratory. Acetone. Acetone is a common solvent used in a laboratory, especially in the world of organic. Ethanol, that I'll abbreviate ETOH. Methanol, that I'll abbreviate MEOH. All of those are very common solvents that we use in a lab, and we can talk about the process of solvation if those are the solvents that are going to start breaking up these other molecules that we're going to bring into the picture. All right, so just a terminology kind of language lesson really here is that all that is. And here's an image that you are seeing the process of solvation kind of right in front of you. So this is solvation of a polar compound by water. And notice that this polar compound in here is going to be negative. I mean, I see that negative charge right there. And look at how they've kind of ordered up these molecules. These are water molecules around them, and here it looks like these big oxygens in the center are going to be negatives, and then these are going to be the little tiny hydrogens that's going to be there. And those tiny hydrogens, those are going to be the positive pieces. So the water molecules begin to come in, and that's what you're seeing in this picture. They begin to start ordering themselves up around this polar compound. And if you take a look at these water molecules, they're kind of coming in. Okay, they know that there's going to be some charges in here, but they're not quite ordered the right way yet because this is a negative, and that negative and this negative repel. So that oxygen would go that way and that molecule would go that way. That's not good for the process of solvation. So over time, these water molecules will begin to orient themselves in the proper way, and they will align their partial positive hydrogens to align with this negative polar compound piece that we have here inside of this container or inside of the beaker and so forth. All right. So this is the final ordering of water, and all of this has extreme order that's associated with it at this point. So water will continue to do this. It will continue to organize. It continues to line things up the way that it needs to be lined up. And then once that process happens, all of my crystals now are invisible to me because that solid has now fully dissolved, and that's this process of dissolving. So it's dissolved, it's soluble, it can mix in with the solvent, and then it slowly dissolves and disappears in front of my eyes. It goes into solution. So that is the process of solvation, and that's something that has been talked about in general chemistry, of course. At least, once again, I hope that it has. All right, so what's not been talked about in general chemistry? Well, a little bit of organic topic maybe. So we have been focused on this field of alkanes, right? And alkanes, we said, were all carbons and all hydrogens. And we've already said that these things, if they're just carbon and hydrogen, they are nonpolar. So the question here is, are they soluble? Well, maybe, right? Because sometimes organics can be solids. So the proper term there would be soluble. Are alkanes soluble in water? Or if they're liquids, because liquid compounds and reagents are very common in organic, are they miscible in water? All right, so these are the questions that we have to answer. We have to get familiar with the solubility. That was one of those 4 things that I told you that we would talk about. So most alkanes that are less than 30 carbons. Okay, where are we going with this? Under 30 carbons, which is a very common thing that we do in a lab. We don't really work with anything larger than that too often. They have extremely small densities. And water has a density value. In general chemistry, they have told you that the density of water is 1. Well, that's a lie. It is not. I'm sorry, it's not a 1. Again, this is a rounded number in a general chemistry class that they use for convenience. The density of water is actually 0.9997 or something close to that, depending on the temperature of the room that the water is in. Yes, temperature has a fluctuation on the densities. Okay, so what this means is that alkanes are nonpolar, and most of the alkanes that we use in a lab that we commonly talk about have extremely low densities. And they are lower densities than water is going to be. So in a beaker, if I take a solid or if I take a liquid, if I take a solid, it is not going to be soluble. A solid alkane, less than 30 carbons, that's just hydrogen and carbon only, so the majority of them, they are not going to dissolve in water. Sorry, folks, they're just not going to. What you would see is water solvent, and you would see crystals of that alkane, maybe either down at the bottom or maybe up here floating on the top. One or the other, but they're just not going to be soluble. They need a little bit of help in order for that to happen. Okay, so what if we're talking about liquids? What if I dump the liquid into water? Well, those are not miscible, and I'm going to form 2 layers each time that begins to happen. Again, we're talking about alkanes. We're talking about carbons and hydrogens that are nonpolar, and I'm putting it into a polar solution. They're going to separate out. Like does not dissolve because there's no things here that are alike. They are different. So these liquids are not miscible. And almost every single time, the alkane will be on top and the water layer will be on the bottom. And the reason for that is the density. The densities less than 30 carbons are lower than water for the most part. And if they're lower, well, they're going to separate. And if they separate, is there an order? Yes, there's an order to it. And it's the most dense on the bottom and the less dense on the top. So alkanes will typically settle toward the top of this layer, and water will typically settle to the bottom of the layer. All right, so that's really how organic compounds behave in a beaker of water if we try to dump it into that beaker. Okay, well, here's another story though. We have not just limited our discussion with alkanes only, have we? We've also talked about things like alcohols. So alcohols are going to be a little bit different. You know, alcohols have this group and it has an OH here at the very end. Alcohols are two faces. Okay, they're two-faced friends. They're going to look at you and they're going to be all buddy-buddy to your face. And then by the time they turn around and make it to the end of the hallway, they're going to be buddy-buddies to your worst enemies. And then they're probably going to talk about you too at the same time. Well, I call alcohols two-faced because here alcohols have a part of them that is really trending non-polar. These are all the carbons and all of the hydrogens that we saw in a traditional alkane. But on this side of the molecule, that's their two faces. This is a polar piece because this oxygen has some free sets of electrons on it, right? And those free sets of electrons are negative, and therefore that oxygen could become slightly negative, and now we are truly talking about polarity. Well, alcohol and water do mix. Okay, we're not going to call that soluble. We're going to call this miscible. You know that. Alcohol and water mix. I mean, go ask any bartender behind the bar if alcohol and water mix. I mean, this is how we make mixed drinks, people, okay? So alcohol and water mix, but you need to keep in mind that alcohol has some non-polar tendencies to it because there's carbons and hydrogens that are there, but it also has polar tendencies, which are the OH groups. So alcohols can form hydrogen bonds. That also means that they form dipole bonds. And that also means that they do really well in polar solvents. That's kind of what polar solvents need. But the problem here is that alcohols in this field, size does matter. So if I take something like methanol, which is CH3OH, it's pretty tiny, isn't it? Poor little methanol. Here we have a CH3 group to the left, just a little C and 3 hydrogens. And then we have this OH group. So this really is kind of regarded almost like half and half. I mean, yeah, it's got nonpolar tendencies, but polar is just as obvious. And then we have ethanol, which is drinking alcohol. So CH3CH2OH. We increase that carbon count. Well, when we increase that carbon count, we increase the non-polarity of that molecule. But it still has a polar piece. That doesn't really go away at this point. So methanol does a great job dissolving in water. Ethanol does a great job dissolving in water. Well, the next one would be propanol, CH3, CH2, CH2, and OH. We've increased the carbon again. We've increased the non-polarity of the molecule. But, folks, we still have that OH group. So propanol does a very good job being miscible with water. And then we have isopropyl alcohol, right? CH3, CH, CH3. There's my iso unit, and then the OH that kind of sticks off there in the middle. Well, that's rubbing alcohol. We know rubbing alcohol does a very good job dissolving in water, or is miscible in water. But notice I didn't say soluble. Okay? So size matters here because there's going to get to a point where an alcohol does not dissolve in water anymore. And that position is anything greater than 4. So 1, 2, 3, and 4. Butanol, CH3, CH2, CH2, CH2OH. Butanol does an okay job. It's okay with water. They are miscible for at least a long period of time. And any isomer of the butanol category would also be miscible. But anything greater than 4 will start to lower the polarity, the overall polarity of the molecule, and therefore we would regard these as not miscible with water. That's our dividing line with the alcohols. So if I bring in an alcohol with 10 carbons, nope, sorry, it's not going to work. You're going to get those 2 layers, and depending on the densities of those 2 layers, one's going to go on top and one's going to go on the bottom. I know it has an alcohol, but that alcohol group, that one little smidgy alcohol group, it can only do so much, right? And then after a certain point, it's just going to get overwhelmed. Everything else on the molecule is just going to take over, and that alcohol group has no power any longer. At least it doesn't have strong enough power to pull it in a solution that is polar. And 4 is the cap for alcohols. The other thing that I want to say about alcohols as well before we go on to our next is that alcohols can be branched, just like any of these other molecules. And anytime branching begins to happen, you actually increase the miscibility with water. Once more, it goes back to that whole concept that the longer cigar-shaped molecules, well, they can overlap a little bit better. Their forces between the two overlap much more, and therefore they can fall out of solution and they can form their own layer. They prevent each other from getting miscible into that solvent. Well, branching disrupts that whole order. So if I have a alcohol that is a straight chain alcohol, 1, 2, 3, 4, 5, and 6 with an OH group, and then I have an alcohol that's 1, 2, 3, 4, 5, 6 with an OH group that hangs out, and I'm giving you a question on which one is more miscible in water, you're going to tell me the more branched one is going to be more miscible in water. This part of the molecule that is nonpolar, this nonpolar piece doesn't overlap. It can't hang out with other parts of the molecule as well because there's branching that's going on. Things are not ordered. Things are not organized. And because of that, the OH group has an easier time dragging that molecule into the water solution and say, you're staying here. You're staying put. You're not going to separate out. You're not going to go on your own little merry way and start your own life yet. I'm still the boss of the family. I'm the OH group, and you're going to do what I tell you to do. And that OH group drags those molecules into the water layer, and they are a little bit better as far as miscibility goes. So branching does a very good job in improving the miscibility with water or something else that's aqueous or polar. I keep saying water because that's the most common one, but anything polar behaves the same way, right? Now, let's talk about the other groups because there were other groups that we have mentioned. The other group is going to be ether. Ethers are very similar to alcohols, and the reason is because it's an ROR, and that O has some free pairs of electrons. All right, so that oxygen it does have polarity with it. It can participate in solubility and miscibility portions with aqueous polar solvents like water. The problem here, though, is that there's carbons that are flanking both ends. There's one to the left and one to the right. So, with that said, ethers, 3 is going to be the cap here. All right, so anything that's less than 3 does a very good job being soluble in water or another type of polar solvent. All right, so there's kind of the trend with the ethers. They are soluble, but you got to look at your carbon numbers, and you got to look at your carbon numbers in order to determine how much non-polarity is associated with those molecules. So O can do the job just like it did before. The problem, it's bringing 2 things into that liquid solution, not just one. The other group that we talked about were amines. So amines, we've talked about primary, secondary, and tertiary amines. Primary amines are much more soluble than secondary amines, which are much more soluble than tertiary. The reason is due to the hydrogen bonding that can happen here. All right, so here's a primary amine, and here we have a hydrogen bond and a hydrogen bond. We also have a free pair of electrons that are there. So because of that, it does have some polarity issues, and it can go inside of a polar solvent, and it can hang out pretty well. Again, though, we're looking at carbon number versus polarity. So secondary, not as much. The reason is because that nitrogen only has 1 hydrogen that can participate in hydrogen bonds. It still has the free pair, but this nitrogen is going to have a harder time getting into and staying into a polar solvent just simply because I'm removing a hydrogen bond away from it. And then tertiary, same deal. I get 3 R's that are connected to the nitrogen. There's no hydrogen bonding at all. The only thing that I have to rely on here is a free set of electrons. So the order of amines, primary, secondary, tertiary, and here we often say 4-5. 4-5, just like with alcohols and ethers, we're kind of in the same realm here. So 4 and 5 carbons. If it's larger than 4 or 5 carbons, then I'm really playing more on the fact of it being a non-polar molecule and not just a polar molecule. So larger than 4 or 5 carbons, absolutely not. These things are going to be a little bit more stubborn for you, and we're going to say they are not miscible or they are not soluble, depending on if they're a solid or a liquid. And finally, alkyl halides. Alkyl halides were your chlorines and your fluorines and your bromines and so forth. So these are also somewhat, I'm going to put here, somewhat soluble and miscible. RF is going to be the most miscible out of the bunch. And again, it's due to electronegativity. It's due to electron greediness. You know, there's more polarity that's assigned there in a way with fluorine. So because of that, it has an easier job going into a polar and an aqueous type of solvent. So RF is going to be the greatest versus the other halogens that are down that group. And they are ranked in the same order that they're written on the periodic table. All right. Once more, we often look at 3 to 4 carbons here. Same kind of ballpark figure, not a big deal. If I'm going to ask you these on a test, I'm not going to kind of straddle the line of 4 or 5. I'm going to give you something small, and then I'm going to give you something big. And then I'm going to say, are these soluble, yes or no, and then write down the reasoning that you had in order to rank your question the way that you did. So I do not like to play that fence line. If I'm going to give you these types of questions, it's going to be very obvious based on these rules what I want you to answer. All right? So no tricks up my sleeve here. That's just the way that I roll. That's the way that it's going to be. All right, so if we take a look at a couple of examples before I end this video, here's a table, and it really breaks down the halogens, and it shows you the solubility of the halogens as we go through. So on the very top line, you're seeing fluoride, chloride, bromide, and iodide. Notice that the fluoride molecule is very soluble, and then the iodide molecule is slightly soluble. So the solubility does change, But again, we're playing off of an alkyl group, which is mainly nonpolar, as well as a halogen, which has free pairs of electrons, that is a polar top end of a molecule. So we're going to see some solubility, and we see that in the very first line. As you go down that chart, look at what they've done. They've taken one carbon, now they've increased it to 2, then they increased it to 3, and then they increased it to 4. So what you're seeing in the very first column over here to the left-hand side is that this one with 1 carbon's very soluble, and then this one with 4 carbons, it is insoluble. So they're telling you, listen, this ain't going to do anything at all for you. Nothing at all, period. So this is the way that we begin to rank. And once more, it will be very clear on what I want you to do when I want you to rank these types of problems as far as solubility goes. All right, so here's an example problem, and it says rank the following compounds in each set from the most soluble to the least soluble in water. So for part A, what I'm looking for here are really free pairs of electrons. I'm looking for polar groups. The more polar groups that I have, the better off this is going to be as far as going into solution with water. All right, so on part A, the very first one, I get some free dots that are here, and I also have some free dots that are here. OH group, I can't forget those free dots on that oxygen. And then here, goodness sakes, I've got 2 sets here, I have 2 sets that are here, and I also have 2 sets that are there. All right, so now that we have assigned those electron dots, I can easily rank these from the most soluble to the least soluble out of the 4. So this one has the most oxygens. That's always a good key, meaning it also has the most electrons that are pairs. So this is going to be the best one to be placed into a water or aqueous environment. This is going to be number 2. That has the next in line as far as polarity goes. Then this one at least has some free pairs of electrons. That would be number 3. And then finally this one, it doesn't have any at all, so that one's going to be number 4. For B, here I get a chlorine, and then I have an OH group, and then I have an OH group here and an OH group there. And if I'm looking at the number of carbons, I see 3 there, 4 there, 4 there. All right, so out of these 3 choices, this one seems to have more polar groups on it, right? I see an OH group that's there and an OH group that's here. Both of those are strongly polar, and those are basically a diol. There's 2 alcohols here. So this is going to be ranked number 1 for that purpose. Now I'm comparing the chlorine to the OH group. That OH group, again, is very alcohol in nature. This is going to go number 2. And then finally for B, this chlorine, this is going to go number 3. So I want you to realize that it's not about the total number of electron pairs, as you can see here, because it's all about the types of bonding. The OH groups are better bonding to an aqueous solution, and that's because these form hydrogen bonds, all right? And those hydrogen bonds greatly increase the polarity of that particular type of functional group. The chlorine does not have that. So that's why this is ranked as number 3. Even though it's got 3 sets of double bond, or 3 sets of electrons, 3 full sets of electrons, it doesn't mean anything. It's all about the types of bonding that can happen here. So alcohols are going to be the best ones to be placed in a water solution at this point, or a polar solution. And then the alkyl halides are going to be the worst that's going to be placed in that solution. All right. What would come next would be amines, because amines can actually participate in hydrogen bonding as well. And then ethers would come after that. They cannot participate in hydrogen bonding. They do not have hydrogen that's attached to an NO or F. Now, if they are placed in a solvent that has an H on an NO or F, then they can participate in hydrogen bonding, because they provide the second NO or F that they would need in order to complete that hydrogen bond. But there's kind of the order, roundabout order in a way, as far as solubility goes in a water or in a polar solvent. All right, so that's how we would answer some of those questions when they would come around and roll up on us. All right, next one. The effectiveness of a barbiturate as a sedative is related to its ability to penetrate the nonpolar membrane of a cell. Which of the following barbiturates would you expect to be the most effective sedative? All right, so this is letting me know, okay, I'm looking at these two compounds, and the directions are really in terms of pharmaceutical here, right? So maybe pharmacy related, maybe medical related. So these two compounds are going to work really, really well if it can penetrate the nonpolar membrane of a cell. So what that means is that out of these two choices down here, the more nonpolar that compound is going to be, the better that's going to be as far as transferring to where it needs to go to and providing its mechanism that it needs to the site of the location. So out of these two choices, I need to figure out which one is more non-polar. All right, so I begin to look at the differences here. That's how I answer this question. This ONH, is also the same as it is here all the way around. So these two are identical parts of the molecule. They do not want me to look at that. What they want me to look at is basically the piece that they attach at this position. So out of these two choices, which one is going to be more nonpolar? And the answer is this one. This one's going to be more nonpolar because there is a longer branch or more carbons and hydrogens that are located here. In addition, look, this is a 2-carbon piece right there, an ethyl group. This is also a 2-carbon piece. So actually, the only group that they want me to look at is this one right here. That's it, folks. Just that one right there. And this is more carbon, more hydrogen, more nonpolar in nature, so therefore this one would be a better drug for my sedative. And it's for that reason alone, because the directions tell me it plays off of nonpolarity. Next one, which of the following would cyclohexane have the lowest solubility? All right, so cyclohexane, what is that? Well, that is a 6-membered ring, and that's it. Nothing more than that. There's no functional groups, there's no OH groups, there's no NH2 groups, there's no O's, there's no free pairs of electrons, nothing. So this is a very non-polar molecule. So the directions say lowest solubility. That means which one of these would be the worst? All right, well, here, pentyl alcohol, 1, 2, 3, 4, 5 with an OH group. Diethyl ether, 1, 2, and then I have an O, and then 1, 2, so there's diethyl ether. Ethanol, which is 1, 2, and then an OH group, and then hexane. So 1, 2, 3, 4, 5, 6. Well, out of these 4 choices, hexane's actually the best solvent. Okay, cyclohexane is nonpolar, and out of these 4 choices, this one is the most nonpolar out of the bunch. So this one would actually be the best. So if that's what the question said, that's how I would determine that. Now, I need to look at the other 3, and I need to figure out which one is the most polar out of the bunch. Well, I know that alcohols now are more polar than ethers are. On the kind of the same number of carbons and hydrogens, that's how we regard those. So the alcohols are going to be my questionable ones. These are going to be the most polar out of the bunch. Now, out of the 2 alcohols that are listed, one is pentyl, one is ethanol. And we said that pentyl alcohol is the fence line, okay? Anything greater than 4 carbons, we said, was not very appropriate for an aqueous solvent or a polar solvent. The nonpolar piece of those alcohols begin to outweigh the OH piece of the alcohol. So ethanol is going to be more polar than the pentyl alcohol is going to be because it has less carbon, less hydrogen, less nonpolar characteristic. So out of these 4 choices, ethanol would be the worst, and that's because it is the most polar out of those 4 choices that they give me in that question. All right, so that's the story with solubility. I wanted to do one video on solubility and that's it, and I did that. However, it took me about 40 minutes in order to explain. Hopefully you get the gist of solubility as well as miscibility, and being able to determine where these organic molecules are going to go and why they go in the layers that they do go in as far as polarity goes and miscibility and solubility goes. All right, so with that said, in the next video we're going to turn our topic to something else, and that's going to be something that we call conformations. So conformations are going to be something pretty big deal in organic, and we're going to spend a couple of videos on conformations of alkanes, and I'll kind of explain to you what this means. So we're getting ready to open up another can of worms. You probably aren't going to like it. I don't like it, but it's what comes with organic. That's just the way that it is. So conformations of alkanes, that's what's coming up.